So what is solid modeling first? Solid modeling is a very important issue these days, as you know. If you want to do, let's say, a graphical application, if you want to manufacture anything, you need to model your thing actually, and then try to start other steps of manufacturing. Or if you are doing any, let's say, animation, simulation, modeling is still a useful tool in such application. So what is our purpose in solid modeling? We would like to actually represent, the manipulate, and sometimes reason about the 3D shape of physical objects. And another issue is that we need to be using computers. It started around 1970s, and after then it developed a lot. Actually, we have now more powerful things, more powerful tools, software. Even we have some, let's say, special robotic type of pens, and with the help of them you can do some haptic design and have more, let's say, powerful models. And we are actually adding more properties every year to these software, and then try to use this software in different fields, in manufacturing, architecture, in material science. We are, for instance, modeling materials, the details of the materials. We are even modeling some specific medicine, biomedical equipment, biological engineering. They are modeling some cells, some tissues. So solid modeling is quite important. And these days, with the introduction of Industry 4.0, we have virtual reality and augmented reality in these things. Obviously, you need to use some modeled, let's say, objects. And with the help of these new applications, now we will have more powerful, we need to have actually more powerful computing platforms. Otherwise, for instance, if you consider the virtual or the augmented reality applications, without powerful computers, they will not be possible. But right now, with the help of these special graphical processing units, CPUs, we have these capabilities, and we can expand the actually range of solid modeling applications. And obviously, in near future, you have more modeling tools, new techniques, and analysis will be added to these technologies. And with the help of, again, the solid modeling, we can further perform some analysis on the models. We can divide them into some smaller finite elements, and then perform maybe, as you know, thermal analysis, fluid analysis, or mechanical analysis. And we have many tools, as I mentioned, and we will be focusing mainly on the modeling part in this chapter, and try to see different types of solid modeling approaches, and you can select the best type according to your, let's say, application. And we have some procedural and declarative type of representations in solid modeling, and they are quite popular these days. In addition to these, we can even do some geometric programming by using some useful programming languages. You can even design highly complicated parts without using, as let's say, conventional CAD tool. Instead, you can do your program, you can write some special scripts and try to generate more complicated parts having very small features. And this is especially used in architecture these days and additive manufacturing. Another issue about solid modeling is that after the beginning of, again, 1970s, we always assumed that the solids, actually the parts we are designing, all have homogeneous interior. We didn't focus on the inhomogeneity or heterogeneous interior structures, but the thing is that we all assume that the interior of these model parts are always solid, and we don't have any gaps, any porosity inside them. But these days, with the help of additive manufacturing, we can have some structures with inhomogeneous interiors, as you see, like this one. And that's why actually some software tools need to be actually improved so that you may have more complicated interior structures instead of having solid interior. You may have different ways to represent designs you have. For instance, you may use graphical user interfaces like our conventional CAD tools with the help of some buttons, some other input, let's say, regions. You can easily model complicated shapes. Another thing you can use is the application type of interfaces. In such interfaces, you don't see anything on your screen, but you have your library imported into your application. And by using the functions and some other properties of the library, you can do and complete your design, even if it's a complicated one. Another thing is we may use some plug and play type of, let's say, software tools in our design and in our analysis applications. So what is that actually? Then this type of plug and play systems, we have a kind of a communication between the software. For instance, we may have a CAD software, and on the other side, we may have a computer engineering software. And these two might be communicating during the analysis all the time. Instead of having having no connection, these days this is preferred since you don't need to do any conversion, you don't need to transfer any files, and with this approach, you'll not be actually, you don't need to adjust the meshes or spend more time on the outer surface. With the help of this communication between the design and engineering software all the time, you decrease the time spent on the meshes, time spent on doing some primitive, let's say, settings. So this is the feature of actually CAD and computer engineering software. So they always ask questions to each other and do their, after they get the answers, they do their assigned tasks. Any questions, guys, regarding these issues? The representations type of solid modeling, or the way we access them by using graphical user interfaces, application interfaces, or with plug and play type of approach. No questions? Okay. So what are the main types of representation? Now we will be going into some details. We'll discuss many solid modeling representations, and the most popular one is constructive solid geometry, and we love to use this abbreviation CSG, constructive solid geometry. So what we do in this type of approach, in this type of representation methods, we try to represent the solids. This is actually the final solid we want to have at the end of our representation, let's say. What we do, we start with basic geometrical entities like a cube, sphere, cylinder. So these are, as you see, the fundamental, the basic geometrical entities. And then what we do some union, intersection, and sometimes take differences. So by using these just three main operations, we can obtain more complicated designs with the help of the solid construction solid geometry approach. So if you look at this tree, it's a kind of a binary tree, and what we do, we have leaves, as you see, and these leaves are processed with the help of the operator we have in this internal node. So this is a union. As you see, that's why what we do, we combine, we do a union operation between these two cylinders, and that's the result of it. And then now we have again two leaves, left leaf and right leaf here. Again, our operation is a union. So we simply union these two and have a more complicated shape. And if you look at the left-hand side, we have a cube, a sphere, and we need to take their intersection. So if you do it, if you take the intersection, that will be the result. And after that, what we are doing, we have a subtraction operation or a kind of a difference operation. So we subtract this green part from the red one and obtain the final shape. So this is how we do if you are following a constructive solid geometry approach. In the second type of representation, it's called as boundary representation, and things are not that complicated. What we do, the history is not important. We don't actually care about the history. If you look at the previous one, you know the history of construction, right? By looking at this tree, you can state which process is done first and then the second one and what is the final, let's say, operation. But in the boundary representations, we don't have such information about the part. We don't know the history of this part, how it is constructed. It's not important for us. The most important part is the boundary itself. So we try to find a way to represent this boundary by simply using the vertices, edges, and faces. So if you look at this simple tetrahedron, we have, as you see, 4 vertices, and we have some faces. We have edges, as you see here, and we try to represent a solid by using just the vertices, edges, and faces. As I mentioned, we don't care about the history, how this one is built. This one is another type of representation, the third one, mesh representations. And this one is somehow related to the boundary representations. Since in the meshes again, our main aim is to represent the boundary by using planar polygons. So these polygons might be triangles, might be quadrangles, might be hexagons, it doesn't matter. So the thing is that we need to use such planar polygons to represent such complicated surfaces. But the problem is that once you use such planar polygons for especially curved or formed surfaces, we will have some errors, let's say representation errors, and the topological information will obviously be reduced. Or sometimes it will not be represented explicitly, but it will be represented implicitly. Then we have another type of representation. This is spatial subdivision. You see an example here. We have a complicated figure, a kind of an animal here. And the thing is that we are trying to divide this, let's say, space into smaller portions. If it's a kind of a cube, let's say, then what we do, for instance, we try to divide it into 8 pieces. This is how we do the subdivision. And for most of the time, we prefer to use unit sizes, but there are also some applications, some different variations of this representation method where they use irregular shapes. They don't just have a fixed, let's say, element. They have a larger one, a smaller one, a medium one. So it depends again on the type of application you are working on. Any questions, guys, about these types of representations? Constructive solid geometry, boundary representations, mesh representations, and spatial subdivisions. Any questions regarding these methods? No? Okay. So let's focus on the first one, the constructive solid geometry approach. As we mentioned in the binary tree, we said that at the beginning of this construction, we make use of primitive, let's say, blocks. What are they? We have a rectangular block, we have a sphere, we have a cylinder. Sometimes we need to use cones, and sometimes torus. But these two are less used compared to the other ones. Most frequently, we prefer to use kind of a box and then a sphere and cylinder. But obviously, there might be some more types of primitive solids. Again, this is very less commonly used. So our main focus will be on the first three. And by using actually some simple methods, we can generate various types of structures. So what is that operation? If you use a sweep operation, we can cover any volume and try to obtain these primitive blocks or more complicated blocks. Even you don't have such primitive or the block you are looking for in the software, then you may design yourself a new block with the help of the sweep operation. So what is a sweep? We need to have a kind of a contour in space. And then what we do, we simply move this contour in the space. And the region or the volume covered by this contour will be actually the solid we are trying to model. And then we have other operations, but there are kind of variations of sweep. So the fundamental operation is sweep, and then extrusion, as you see, is a very different, simple way of sweep. What we do, we have this time a straight line instead of a curve or a complicated, let's say, profile. In extrusion, you need to have a straight line, but the rest is the same. You again start with a close contour in space and then move this contour in space in the direction of this given line. And again, the covered volume will be the solid we are modeling. Then we have another operation, but again, this is a variation of sweep. It's a circular sweep and it's called revolution. This time what we do, you have the contour, but you move this contour along a circular path. And this is called as revolution. And with the help of it, for instance, we can easily obtain a torus, right? And even we can obtain the other shapes, but this is mostly used for obtaining torus-like shapes. And then what we do, once you have these models, you can simply perform some Boolean operations as I've shown you in the binary tree. You can join them together, take the intersection sometimes, or sometimes take the difference of a part from the other part, so that at the end of all these operations, you will obtain the actual model you are looking for. Any questions, guys, about these fundamentals of constructive solid geometry? Okay, let's continue. We don't have, obviously, a single representation of solid shapes. You may have different binary trees, but the result of the construction might be the same. So we don't have a unique method for obtaining a single shape. And for modeling, actually, we prefer to use such constructive solid geometry things, but for visual representation, we prefer to use boundary representations. So for modeling, constructive solid geometry is easier, since you start with simple shapes, join them, take difference, take intersection, and try to obtain the final shape. But while showing these complicated shapes, we don't need to actually deal with the history of these parts. Instead, what we do, we focus on the outer representation and try to show you the actual product on your screen. And this is the way actually CAD software are doing. They simply use constructive solid geometry for modeling, but for representation purposes, they prefer to use boundary representations. As we have seen, this was the second type of solid representations, solid modeling representations. And the advantage is that with the help of these, we can have faster rendering. So the graphical processing units actually prefer to do operations on the boundary representations instead of doing operations on the constructive solid geometry. So this is how most of the software is working. So these are the same issues we mentioned. And in these operations, in this construction, actually, we simply use a set theory. This is not complicated. The set theory is about this actually diagrams. We take the intersections, subtractions sometimes, or join them together. So this is the fundamental of constructive solid geometry. So how we are going to model such parts with the help of constructive solid geometry? We said that we have primitive blocks, primitive, let's say, geometrical entities like a box or cylinder or a sphere. We need to have some coordinate systems for such simple entities. If you look at these, this is a block and we have a cylinder. As you see, this one has dimensions, width, depth, and height. Width is in the y-axis, depth is in x-axis, and height is obviously in z-axis. And the origin is, the default coordinate system is located at this back side of the block in this configuration. And the important part is this, the value in the y-axis is represented with as the width of the part, width of the block, and the value in the axis actually gives us the depth of the block. And then if you look at the second example here, the cylinder, we need to just have two parameters to define a cylinder. What is that? Obviously the radius of the cylinder, and the height of the cylinder. The thing about the coordinate system is that it's located at the center of this cylinder. So this is the origin for our cylinder, but it is at this back side for the block. As I mentioned, this is giving actually us the y value, this is x, and this is z. Any questions, guys, about these simple geometrical entities? So then what we do, if you remember the binary tree, we had such simple geometrical entities at the leaves, and then we try to do some Boolean operations with these leaves. It might be an union operation, intersection operation, or an subtraction operation. Well, once you do these operations, then you need to update your coordinate systems. But in starting, at the beginning of these operations, you will always assume that they have a default coordinate systems. So we have an example here. So what is that? This one is actually generating a block. This was a y, if you remember, width, depth, and height. And then we do a union operation, but union is performed with the help of this moving operation here. In the moving, what we do first, we create a block here, and this block is moved by this amount. This is x, y, z. So we first create such a block and then move it in the space by these, let's say, values. X is 0, Y is 4.5, and Z is 1. So we shifted in Z by 1 unit, and we shift also the block in Y-axis by 4.5 units. And then once you do this generation of the block and moving operation, then you need to do the union operation. Now we will see the result in a moment. And we have an extra, let's say, operation. What we do, I'm sorry, this is an subtraction operation or a difference operation. So what we do after you join these two blocks together, you take the difference of the part of this part from the first, let's say, expression. So what we do here, we kind of generate a cylinder first, having a radius of 0.75 and then height of 1. And as you say, this is also moved to a different direction, different position. So you need to first do these operations, generate the cylinder, move it to this position, and then take the difference of these two, let's say, separate parts. So let's focus on here. We said that the first operation is generation of this block, which has an width of 8, depth of 3, and height of 1. This is actually it here. It has a width of 8, depth of 3, and height of 1. Okay, and the default coordinate system for this shape is at this, let's say, back corner. This is the default coordinate systems according to the definition of our block in this constructed solid geometry approach. And then what we do, we create another block by, again, width, depth, and height. This is, as you see here, the width is 2, and then we have a depth of 3, and a height of, once again, 3. But this time, we are not keeping it as it is. We are doing a kind of a moving operation, and this is how we do the movements X, Y, and Z. So in X direction, we don't move it, but in Y, we move it by 4.5. So this was, let's say, 0. So we need to move it in this. Let me have an arrow here. This is Y direction. And I know that this is the origin for each blocks generated. First of all, let's focus on 1. Since this block is moved by 1, that's why it resides on the initial block we have generated. Okay, I think Z is clear, and X is also clear since we don't have any shifting operation in this X direction. That is fine. And then we need to move it in Y-axis by 4.5, and this is what we do here. So this part is, so this is the, let me show this dimension. What is that dimension, guys? What is the length of this segment? Yes, it's simply 4.5. So we have 1.5 left here. So you may do a kind of a check operation. This part is 1.5. Now we have two blocks union together. So this is important. We generated the block, we shift it to a different position, and then do an union operation with the first block which is residing underneath. So right now we have a single part, a kind of a T shape, not exactly, but similar to a T shape. And lastly, what we are doing, we need to take the difference of the initial shape with a cylinder. So what we do first, we need to create the cylinder, shift it to the appropriate position, and then do the subtraction operation. So this is the radius, as you know, and this is the height. Since I know that this part is 1, the height of this block is 1, so I don't need to have a longer cylinder. We don't need to have. You may have, but it doesn't. It's not important. Right now, we are assuming that we have an exact cylinder with a height of 1 unit. So this is generated, and this time, as you know, our origin is at the center of the cylinder. So at the beginning of this operation, our cylinder will be at this point, which is again 0, 0, 0. So we are generating this cylinder right at that point, okay? So at that origin, we have a cylinder with a radius of 0.75 and a height of 1. So that's why if you want to have such a hole at this part, you need to do some, again, moving operation. So what we do, we need to move it in X by 1.5. So in X, it should be shifted by 1.5. And again, on Y-axis, to the right, it should be shifted by 1.5. Another issue is that it should be shifted in Z direction by 0.5. Since if you do not do any shift in the Z direction, what is going to be? We will have half of these actually cylinder underneath this initial union plugs. But if you do a shift in Z direction, then we will exactly have the, let's say, the center of the cylinder at this at the 0.5 point. Z is equal to 0.5. So once you do this moving operation, then the center of your points will be these values simply. Now it's at the desired position, so we can do our difference operation, complete our difference operation, and have this desired shape. So this is how we do the construction in constructive solid geometry. We use simple blocks and their coordinate systems, their, let's say, input types are important. And then what we do, we use simply intersection and joining and difference operations. Any questions, guys, about these this example? No questions? Okay. Make sure that at the beginning of the second lecture you have an empty sheet of paper, a kind of maybe a ruler. You will have a quiz about these, okay? I'm sorry for that. Oops. Sorry, guys. Okay, let me ask once more. Do you have questions? So at the beginning of the second hour, make sure that you have an empty sheet of paper, kind of a ruler, and I will give you a kind of a constructive solid geometry statement, and I want you to do the operations. Is ruler essential? Yes, somehow. If you have it, it will be better, but if you can have, let's say, proper dimensions, that's fine. It's not a must, but it's better you have it. Any other questions, guys?
Can I ask?
Sure.
Are we gonna start always at the origin or the origin of the first block? If you have two blocks and move command, are we gonna start at the origin or the previous block origin?
No, we always start at the origin of the. Actually, you say that in this
Like moving
final
direction.
part, what will be the origin? Yes, it will be the origin of the first part.
Ah, okay. Like I'm asking, like last cylinder, we move it 1.5, 1.5, and 0.5 according to first block or the origin.
According to the first block. So the first block will determine the origin of the final, let's say, representation, final solid. So you define the other parts, other blocks according to the origin of the first one. Okay?
Okay, thanks.
Hocam, I have another question.
Yes, Yiğit.
You said 2 in the y direction when, sorry, in the constructing of the second block, but in the code it says 2 in the x direction, not in y direction. Did I make myself clear?
Do you mean this generation of the block?
Yes. In the shape you wrote 2, but it should be 3, I guess, because you said 2 in the y direction.
According to our, let's say, given representation, according to the rule, the blocks should be represented with width first, then depth and height. And as you see in this coordinate system, we have widths in. Yes, you are right. I'm sorry. Yeah, this should be in y direction. Yes, you're right. The width is no, you're not right. I am right. This width is, if you look at here, it should be 2, and depth is 3.
Yes,
and
yes,
height
I
is
guess.
3.
Sorry, I'm sorry.
Okay. Any other questions, guys? So then I'm clearing the screen and then moving to the next slide. So as you have seen in the beginning of the constructed solid geometry, we make use of such binary trees, and we make use of the primitives at the leaves of the tree, and then we have internal nodes, and these internal nodes are always representing the type of Boolean operations we need to perform while constructing that solid. And at the end of operations, once we have the constructed solid geometry, so what we do, we have the final design and its surfaces somehow defined, and obviously it's also the interior is once again defined, but they are both defined implicitly. We don't have an explicit information regarding the surface of the final geometry, but we have an implicit information. By using that implicit information, your CAD tool will show you the result. Since if you look at let me go back to the tree. Yes, it should be somewhere here. Yeah. If you look at the tree here, we have leaves, as I mentioned before, as the primitives, and then the internal nodes are defining the Boolean operations. And at the end of the operation, at the end of this tree, we will have the final shape. But this tree itself is not defining the outer geometry. So it is just a data structure. By looking at the tree, you cannot have it. You cannot say whether this shape is going to have, let's say, 10 vertices or 10, let's say, faces. We don't have such information available in the tree. So that's why we say that the tree is actually storing an implicit information about the interior and about the exterior of the geometry. So that's why we can say that simply the tree representation is an implicit representation of the solid models. Any questions, guys, about this thing, this implicit and explicit type of representations? For instance, what about the boundary representation? Is it an explicit type of representation or an implicit type of representation? No questions? No answers? So what do you think? One answer from Mithat, explicit but not sure. What do you think? The boundary representations, are the boundary representations explicit or implicit? Yes, Ahmed, why do you think it's an explicit type of representation? Yes, since the surface in that representation method, we are defining the surface with the help of such vertices, edges, and faces. We can simply say that it's an explicit representation, and the surfaces are defined clearly with the help of these vertex, surface, and edge information. But as you see in constructed solid geometry, we don't deal with them. We simply have a tree. We show how this part should be constructed, and that's why this is an implicit representation. Another issue about the solid geometry is that constructed solid geometry is that we are always assuming that the interior is once again homogeneous and it's solid. We don't focus on the special interior structures like this one. We are always assuming that the interior is a solid one and is filled completely with material. So now let's start discussing the boundary representations. The first one obviously is in abbreviation is BREP, boundary representation, and it's representing the boundaries, the surfaces explicitly, but the interior is represented implicitly. Since we don't have any information regarding the interior, by simply defining the outer surface, we are assuming that the interior is again an homogeneous interior, it's a solid. So by this way, we can say that the interior is represented implicitly instead of an explicit representation. So these are the things we discussed. We make use of faces, edges, and vertices while representing the geometries by their boundaries. So now what we do in this type of representation, the edges and vertices are quite important by checking their adjacencies, their neighborhoods with different faces, different edges. We try to actually comment whether it's a kind of a manifold type of object or a non-manifold type of object, which means that if it's a non-manifold, then you cannot manufacture it. We will see an example. We have some rules for that. We need to check the number of, let's say, faces, the number of edges sometimes, and then later comment on the manufacturability of the part. So these are this is a simple example of a boundary representation. As we mentioned, our main focus will be on the edges, like these, surfaces, vertices, and sometimes in different boundary representation methods, the normals are also important. These normals are showing the outer of the part. So by using that information, you may perform various operations. And while representing them in a kind of a file, we need to have information between these neighborhoods, between the adjacency of these faces, edges, how they are connected to each other, which let's say, if you consider this edge, which vertices are actually generating this edge. So in that files, in that representation methods, you need to have such information. Otherwise, it will not be possible to model the physical objects. This is another one, a bit complicated one. Instead of having, let's say, the simple information, having like information about the vertices, edges, instead we may have some parametric surfaces. We haven't discussed them yet, but in the next chapters, we will be focusing on these parametric representations. And instead of having, instead of using simply vertices, edges, or faces, you may use such parameters, and they will be implicitly defining the surfaces we have. Another issue is that in the boundary representations, you shouldn't have any surfaces intersecting with each other or edges intersecting each other. This is not allowed in the boundary representations. They should just touch each other. They may have common vertices, common edges, but they shouldn't be intersecting each other. If you have such cases, then that means your representation is not valid and the CAD software will not be able to process your design. And if you remember, while we were introducing these type of representation models, I said that the CAD software prefers to use actually boundary representations for graphical purposes. For instance, you do a kind of a constructive solid geometry, but the final result is stored as a boundary representation. To make it easier for, let's say, graphical purposes. And in that case, they prefer to perform such union, intersection, and different operations by using BREP systems or BREP representations. And some cases, in some situations, CAD software might be using these two representations at the same time. If you consider, for instance, SolidWorks, I think it's also the same in NX. You have a kind of a history, how you construct the part, but the model you are looking at is a boundary representation, not exactly the constructed solid geometry. Since it will take lots of time, it will be using your processing power a lot. So that's why they perform most of the operations by on the BREP representations, boundary representations. Otherwise, they will require more random access memory, more processing power, and you'll not be able to join many parts together. So that's why some novel CAD tools prefer to use these two representations at the same time. The advantage of constructed solid geometry is that it's easier for the user to construct, to design their models. But for the computers, it's easier to use boundary representations. Any questions, guys, regarding the issues on the boundary representations? So as I mentioned while discussing at the beginning of the boundary representation discussion, there might be some manifold type of representation or non-manifold representation. By manifold, I mean that the designed model can be manufactured. But if you have a non-manifold case, let's say if you have these two parts which are just connected through an edge, and this is a non-manifold example, and you cannot manufacture it. This is a popular example of non-manifold cases. And in the oriented manifolds, we should have always edges which are incident to two faces. So if you look at here, this is an edge, for instance, and it's the incident of two faces. Or considering the vertices, we have vertices at the corners, as you see, and they should be the apex of a single cone of incident edges and faces. So you may simply assume that this is a cone or a pyramid, and the top of the cone or the pyramid is the vertex. And this is valid for the manifold type of objects. But obviously, if you have manifolds, then we should have the non-manifolds. But non-manifolds are problematic ones, and we shouldn't be working on these non-manifold ones. The problem with these is that the edges are usually adjacent to an even number of faces. Instead of having just two, they may have, let's say, 4 faces. Like here, for instance, I had shown you with my pieces. Here is the schematic drawing of that. We have 2 pieces, one up, one down, and they are joining from this. They have a common edge, and this edge, as you see, have an even number of faces. So this is a non-manifold object, and this edge has an even number of faces connected to it. 1, 2, 3, and 4. And we have another non-manifold property here. As you see, 2 corners are connected from this vertex. And again, this is a non-manifold example, and they are not manufacturable. So if you consider this non-manifold thing about the edges, so if you do a kind of an radial movement like this one, if you move radially around this edge, then what we are going to have, we will have consecutive faces which are alternating bonding the solid interior or solid exterior. So we have this face, for instance, and then the bottom face. As you see here, they are bonding the solid interior. But now, if you consider this face and the one here, the vertical one, they will be bonding the exterior. And then we have 2 other faces. They are representing the interior. And lastly, we have one here, one face here, one face here. And as you see, they are bonding the solid exterior.